Welcome to this lecture. In this lecture, I am going to talk about matrix formulation of quantum mechanics. So in that lecture, I talk about matrix algebra, and in this lecture, I will again talk about some remaining topics of matrix algebra. So here I will talk about transformations and diagonalization of matrices first of all. Transformation and diagonalization of matrices. So I will start my topic with the transformation of basis vectors. First of all, basis vectors and vectors. Right. So first of all, I will talk about basis vectors and then I will talk about the vectors. I also talk about these topics in the course of electrodynamics. In more detail. So these are the basis vectors in the two different frames. In S frame, basis vectors are E1 and E2, and in prime frame means when this frame is rotated with some angle theta with respect to the stationary frame. So that means this prime frame, it is E1 prime and E2 prime. So now, as seen from moving frame of reference, then E1 prime can be written as in terms of E1 and E2. So it is E1 cos of angle between E1 prime and E1 plus E2 cos of angle between E1 prime and E2, right? So that means the cos of E1 prime, this is E1 prime and this is E1, so the angle between these two is the cos theta. So angle is theta, so that's why it will become E1 cos of theta. And here it is E2 and it is E1 prime and E2. E1 prime and E2, the angle between them is 90 minus theta. So this angle is 90 minus theta. Sorry, so I have to write down it as cos of 90 minus theta. Now I will talk about next. Then it can be expressed as E1 cos of theta plus E2 sine of theta. Similarly, I can write down expression for E2 prime, and E2 prime can be written as E1 cos of angle between E2 prime and E1 plus E2 and cosine of angle between E2 prime and E2. So it is E1 cos of 90 plus theta plus E2 cos of theta. So angle between E2 prime and E1, E2 prime because it is E2 prime and E1. The angle between this whole of the angle is 90 plus theta, so that's why it is 90 plus theta. So it can be written as E1 sine theta with negative sign and plus E2 cos of theta. So that means in matrix form this can be expressed as, or if we rewrite these two results, then these results can be written as E1 prime is equal to E1 cos theta plus E2 sin theta, and E2 prime is equal to minus E1 cos of theta plus E2 sin of theta. So in matrix form, this results can be written as that E1 prime and E2 prime must be equal to cos of theta, it is sin theta minus sin theta and cos of theta, and it is E1 and E2. And similarly, inverse transformation, in terms of inverse transformation, these results can also be written as that E1 and E2, it must be equal to cos of theta minus sin theta, and it is sin theta and cos of theta, and it is E1 prime and E2 prime. Let me call it as equation number 1 and this as equation number 2. Or this may also be modified too, that E1 is equal to E1 prime cos theta minus E2 prime sin of theta, and E2 is equal to E1 prime sin of theta plus E2 prime cos of theta. This is equation number 1 and this is equation number 2. Also another thing which we know that a vector remains invariant. Say it is a vector A. Let me call this vector A. This is E1, this is E2, this is E1 prime and this is E2 prime. And this is making an angle theta. Since this vector remains invariant, whether it has been seen from the S frame and or it is seen from S prime frame, but it will remain the same, it will remain invariant. Or in other words, I can say that A vector is equal to A prime vector, right? So for this, let us proceed as follows. So now a vector A can be written as A1 E1 if it has two components A1 and A2, then it can be written as A1 E1 plus A2 E2 and is equal to A1 E1 prime cos of theta minus E2 prime sin of theta plus A2 E1 prime sin of theta plus E2 prime cos of theta. So this modifies to A1 cos theta plus A2 sin of theta, and it is E1 prime plus minus A1 sin of theta plus A2 cos of theta, and it is E2 prime. So this can be written as A1 prime E1 prime plus A2 prime and E2 prime. So that means I can express as that a1 prime is equal to a1 cos theta plus a2 sine of theta, and a2 prime is equal to minus a1 cos of theta plus a2 cos of theta. So in matrix form, this equation can be written as, this is a1 prime, a2 prime, it is cos theta, sine theta, minus sine theta, and it's a cos theta, and it is a1 and it is a2. Let me call it as equation number 3. And in general form, this a prime can be written as a. So here S is known as transformation matrix. And similarly, in terms of inverse transformation matrix, we can express as a1, a2. It can be written as cos of theta minus sine theta cos theta, and it is a1 prime and a2 prime. Let me call it as equation number 4, or it is a is equal to s prime a prime, where determinant of s and determinant of s prime both are equal to 1, and s and s prime, their product is equal to s prime and s, and it is always equal to a identity matrix. So from here we are concluding that S inverse is equal to S prime is equal to S inverse, and also S inverse is equal to transpose of S. So here I can conclude that S inverse is equal to ST, which implies that S is a orthogonal matrix. Now, if we consider two matrices together, sorry, no, not matrix, but I consider two vectors A and B. So this E1 and E2, they represent the basis vectors. It is E1 prime and it is E2 prime. And let me call it as it is vector A and it is a vector B. Right? So what I did, I considered two vectors A and B in S and S prime frame. Then, using equation 3 and 4, we can write that A prime is equal to SA, and similarly B prime can be written as SB. Let me call it as equation number 5, equation number 6, and A is equal to S prime A prime, and similarly B can be written as S prime and B prime. It is equation number 7, and let me call it as equation number 8. Also consider that a transformation matrix P transforms A to B. That means this A can be written as PB, or A prime can be written as P prime B prime. Right? But this B can be written as S prime B prime from equation number 8. Let me call it as equation number 9. And this S prime is equal to S inverse B prime, because S prime I have seen in earlier that it is S inverse. I have used the property that S prime is equal to S inverse, so it is P S inverse B. Also, this A can be written as S prime A prime is equal to P S inverse B prime, and this is nothing but this S prime is also S inverse A prime is equal to P S inverse B, and if I operating both sides by S, then S inverse A is equal to S P S inverse B. So it means this A prime can be written as S P S inverse B, and this A prime is equal to P inverse B, P prime B prime is equal to S P S inverse B. And it is prime is here, it's here, so I missed it somewhere. So it is P is equal to S P S inverse, and let me call it as equation number 10. So this equation defines the transformation of a square matrix P into a square matrix P prime by non-singular matrix S. S is called non-singular because its inverse will exist. And similar equation we have seen in the book Quantum Mechanics by Schiff. That is 4th edition. It is equation number 7.19 in that book. The equation will be that S A S inverse is equal to A prime, right? So it is equivalent to that equation, and it is from the article of transformation and diagonalization of matrices. Then it is stated that the form of a matrix equation is invariant or is unaffected by transformation. Thus the equation AB, let us assume equation CDE is equal to F, may be transformed into SAB, means both sides are operated with this SCDE S inverse and SFS inverse, and which is equivalent to SAS inverse into SBS inverse plus SCS inverse plus into SDS inverse into SES inverse, it is equal to SFS inverse. So then it can be written as A prime B prime plus C prime D prime E prime and must be equal to F prime. Thus the matrix equation is invariant, right? Also, another important note that trace of A must and determinant of A are unchanged by transformation. The first part of this lecture is finished, and in the next part of it I will talk about eigenvalue equation and diagonalization of a matrix. So the next I will talk about eigenvalue equation, and diagonalization of a matrix. So consider a consider a square matrix. Matrix A, and is defined as Aij of order n. And a column vector or the column matrix X of order n such that Ax is equal to lambda x, and let me call it as equation number 11. This equation is known as I'm just recapitulating the things. I'm not talking all these things in more detail because all you have studied it in the BSc course of mathematics. Here, X is called eigenvector of matrix A and lambda is called eigenvalue of A corresponding to eigenvector X. Also, equation 1 can be written as A11, A12, A1n, A21, A22, and so on, A2n, AN1, AN2, ANn, this multiplied by x1, x2, and so on xn, and it must be equal to lambda x1, x2, and so on xn. And this may be written as A11 minus lambda x1, A12 x2 plus A and so on A1 and xn is equal to 0, or A21 x1 plus A22 minus lambda 2 plus and so on A2n xn is equal to 0, and so on. An1 x1 plus An2 x2 and so on Ann xn, it must be equal to 0, or this can be written as in the form of a matrix lambda I A minus lambda I x is equal to 0. Here let me call this as equation number 12, and this as equation number 13. Now it's like a equation, nth order polynomial equation. If you solve this equation or solve this determinant, so that means if lambda i's are eigenvalues corresponding to equation number 11, that is Ax is equal to lambda x, then also if A is a square matrix of order n, I am reframing this equation again, is a square matrix of order n. Therefore, equation 13 is possible if this lambda is a, there is another possibility that lambda is a diagonal matrix whose diagonal elements are lambda I. So therefore lambda can be written as lambda 1 0 and so on 0 0 lambda 2 and so on 0 0 0 and so on, and it is lambda n, right? So that means a matrix we have corresponding to matrix A, we need another matrix lambda, and which is a diagonal matrix, right? So that means we have to use a transformation matrix so that the resultant will be a diagonal matrix. So that's why diagonalization is a very important idea. to get the eigenvalues and the eigenvectors. So thus there is a need to convert A into lambda. Here lambda is a diagonal matrix using some transformations. That means we will use transformation S prime AS as we have studied earlier in the transformation matrix, such that we are getting a resultant will be a diagonal matrix, or I can say that AS is equal to S lambda. Thus A can be diagonalized using matrix S, and this diagonalized matrix must have property that lambda ij is equal to this lambda I delta ij. And there is a note which we have to keep in mind. The note is that this lambda and A are said to be degenerate when two or more eigenvalues are equal. When two or more eigenvalues are equal. Right, so this is one part. Another part is also completed. Now next I will talk about function of matrices. So let us talk about function of matrices now. So let us recall Cayley-Hamilton theorem. So according to this theorem, if A is a square matrix whose characteristic polynomial is relating to eigenvalue equation. So this characteristic polynomial can be represented as C naught, or sometimes we call it as f of lambda. C1 and minus 1, and C2 lambda and minus 2, and so on, Cn minus 1 lambda and Cn. Then this characteristic equation is satisfied by A. Somewhere it was written f of A or d of A, and it must be equal to 0. This characteristic equation must be satisfied by this, or I can write down it as Cnan plus Cn C1, sorry, C naught An C1 it is C naught An plus C1 An minus 1 plus and so on, Cn minus 1 A plus Cni, and it must be equal to 0. or I can say that d of a or f of a is equal to 0. And here f of a is known as a function of matrix. Means every square matrix satisfies its characteristic equation. That's what we are concluding from here. So here we can say that d lambda, it can be written as determinant of a minus lambda I, or f of lambda. Then d of a or f of a, it must be equal to 0. This we are concluding it in the short form. Now let us talk about function of a diagonalizable matrix. Functions of a diagonalizable matrix. So let A is a diagonalizable matrix. And S is a diagonalizing matrix. So therefore, as we have chosen S in such a manner such that S inverse A, S is equal to lambda, or we can say that because lambda is a diagonal matrix, or other way around we can write down it as A is equal to S lambda S inverse. Let me call it as equation number, let me go to the back. Let me call it as equation number 16, and let me call it as equation number 17. Now here the lambda is a diagonal matrix containing eigenvalues of a Now if f is any function of a matrix, then we can write down it as f of a can be written as f of lambda S inverse. Let me call it as equation number 18. Also, we know that any function can be written as a infinite series. So this motivates us to express a matrix in the form of a infinite series. So let me take an exponential function, and exponential function can be written as e raised to power x k 0 to infinity and x raised to power k over k factorial. This is exponential series. So it's an algebraic function. This algebraic function can be written in the form of exponential form. So keeping this in mind, we can define a exponential of a matrix. Therefore, exponential of a matrix can be written as exponential of a is equal to summation k varies from 0 to infinity a raised to power k over k factorial. Now lambda is a diagonal matrix. and is defined as and exponential of this lambda can be written as k is equal to 0 to infinity and lambda raised to power k ij over k factorial, and this I can write down it as k is 0 to infinity. It is lambda I k over k factorial, and this is delta ij, and this is nothing but this is a exponential of lambda I and delta ij. Here I have written its value as exponential of lambda I and this into delta ij. Also, this lambda is a diagonal matrix. Then exponential of lambda can be written as exponential of every diagonal entity we call it as equation number 19. Thus, now consider the series. That exponential of a is equal to I plus a square by 2 factorial and so on, a k by k factorial and so on. And let S be a matrix which is used to convert A into a diagonal matrix. So keeping this in mind, what I will do, I will operate this 20 equation first of all with S inverse and after that with the S in this manner. So it can be written as S inverse IS plus S inverse AS plus S inverse A square by 2 factorial S and so on, S inverse AK by K factorial into S, and this will transform it into their corresponding eigenvalues. So it is I plus lambda square by 2 plus and so on, lambda k by k factorial and so on. So it is exponential of lambda. And similarly, I can prove that exponential of can be written as exponential of lambda and S inverse, right? So this is another thing. And let us do one problem relating to it. The problem is that we have to prove that determinant of exponential of A must be equal to determinant of trace of A. So let us start. Since we know that S inverse AS is equal to lambda, so A can be written as S lambda S inverse. Therefore, trace of A can be written as lambda 1, lambda 2 and so on, lambda n. Also, we know that exponential of A is equal to S exponential of lambda into S inverse. Now taking a determinant on both sides, so determinant of exponential of A, it can be written as determinant of S determinant of exponential of lambda and determinant of S inverse. So its determinant is identity matrix, its determinant is also identity matrix. So that means it is equal to determinant of exponential of lambda. So determinant of exponential lambda, it can be, if I try to solve this matrix, then this matrix gives us the value exponential of lambda 1 into exponential of lambda 2, because it's also a diagonal matrix. So determinant of diagonal matrix is nothing, simply the product of diagonal elements. So that's why I'm writing it as exponential of lambda 1, exponential of lambda 2, exponential of lambda 3, and so on, exponential of lambda n. And if everything is exponential, so it is lambda 1, lambda 2 plus and so on lambda, and it can be written in this form. So this value is nothing but this is the trace of A. So that means I can write down as that determinant of exponential of A is nothing but simply equal to exponential of trace of A, right? So that's what we are getting the result, and hence the result will be proved. And another two important results which we have to take care, or we have to consider. So there are two special notes or the special properties, that e raised to power a dagger is always e raised to power a dagger, and another thing is that e raised to power iota h is unitary if h is Hermitian. Right. So with this brief review of matrix algebra will be completed, and in the later lecture I will talk about Hilbert space and then bracket notations and how that leads to the infinite matrices. So thanks for watching this video.